Hello, I'm Dave Brown. We now continue Teletrain's study on industrial pneumatic technology, which is based on Parker Hannafin's text of the same name. Today's subject is energy transmission using a pneumatic system, which you will find starting on page 15 of the text. First, let's take a look at some of the properties of gases in general. As we've said before, by definition, a gas is a fluid that has neither independent shape nor volume, but tends to expand indefinitely. Molecules of liquids and solids cling together, but molecules of gases do not attract each other. Instead, they are constantly racing around, much like a swarm of bees. If a gas is not in a closed container, it immediately disperses into the atmosphere in all directions. If even a small amount of a gas is put into a container, it will immediately disperse throughout the vessel. To more fully understand gas properties, we need to talk just a minute about heat energy. In solids, heat is found as vibrating molecules. The more violently the molecules vibrate, the hotter the material. In a liquid, the molecules are in contact with each other, but are continually slipping and sliding around and moving in relation to one another. The faster the movement, the hotter the liquid. In a gas, the molecules are already darting about in all directions. But as this activity increases, the temperature rises. And as it decreases, the temperature goes down. If the gas is in a confined space, such as a tank, then an increase in temperature will also mean an increase in pressure. You may have noticed this with your automobile tires. In the morning, when it's cold, the tires will have less pressure than after you've driven on the freeway for a few minutes and allowed them to heat up. On the other hand, if we add heat to a gas and keep the pressure the same, then the volume will increase. This relationship between the pressure, temperature, and volume is expressed in a formula which is called the modified ideal gas law. As you see here, it's stated as pressure 1 times volume 1 divided by temperature 1 equals pressure 2 times volume 2 divided by temperature 2, or P1 times V1 over T1 equals P2 times V2 over T2. The numbers indicate the original and final condition of the gas in this formula. The P, or pressure, is expressed in absolute pressure in pounds per square inch, which means we must add 14.7 to the gauge pressure. The temperature is stated as absolute temperature. Absolute zero is the point at which all molecular movement stops, which is another way of saying it is the coldest temperature possible. At this point, the Fahrenheit scale reads 459.69 degrees below zero. For convenience sake, this reading is usually rounded off to 460. This means we must add 460 to our Fahrenheit reading before we substitute in the formula. The modified gas law isn't absolutely exact, but it is close enough for most everyday calculations. Okay, let's practice using the formula. Let's say we have an air cylinder with a volume of 10 cubic inches. We will put a water cooling coil on the outside, so we will keep the temperature constant. As you can see, this port is open to atmosphere, which means the absolute pressure reading here is 14.7 psia. Since we are keeping the temperature constant with the cooling coil, we can just cancel the temperature out of both sides of the formula, which now becomes P1 times V1 equals P2 times V2. Now we move the piston on the cylinder in until the volume is 5 cubic inches. Then if we substitute in the formula, we have 14.7 times 10 equals pressure 2 times 5. Finally, pressure 2 equals 29.4, which shows us that if the temperature remains constant, the pressure will vary inversely as the volume. This is just another way to say if we decrease the volume, we will increase the pressure a proportionate amount. And just the opposite. If we increase the volume, the pressure will drop a corresponding amount. We must be sure to remember that pressures in the formula are absolute pressures. If the pressure remains constant, then the formula becomes V1 divided by T1 equals V2 divided by T2. And volume of the gas will vary directly as the temperature. That is, increase the temperature and the volume will increase. Decrease the temperature and the volume will decrease. All right, let's examine why these relationships are so. Let's look at a cylinder again. When the piston is in this position, the air molecules are flying around, as we said, like a bunch of bees, hitting each other and the sides of the cylinder. As we compress the cylinder like this, the molecules are closer together and hit each other more frequently, as though we had made the bees mad. The additional collisions of the molecules cause an increase in temperature as well as pressure. If the cylinder is allowed to stand for a while, the temperature will cool to that of the surrounding air, or ambient temperature as it's called. The pressure will, however, remain higher than ambient, since the molecules are still crowded together. When we increase the volume, the gas expands to fill the container. The molecules are farther apart, and hence there are fewer collisions, and the pressure and temperature are both reduced. Here again, after the temperature has reached ambient, the pressure remains lower than it was to begin with, because the molecules are still farther apart. The main reason that compressed air is used in industry is that it's a convenient form of energy. Here we have a tank which is filled with air at 100 psi. We then have potential energy stored in the tank. Air under pressure will always flow to an area of lower pressure. If we open the valve on the tank, we see that the air will flow out until the pressure in the tank equals atmospheric pressure. Now let's pursue that idea one step further. We have two tanks, the same size. We connect the two with a pipe and put a shutoff valve in the line right here. With the valve closed, we build the pressure up in this tank until it's 100 pounds per square inch absolute. Now in this tank, we build up pressure to 50 psia. I think you can already guess what's going to happen when we open the valve. You were right. The air that's compressed to the higher pressure will start to flow into the lower pressure tank. This flow will continue until there is equal pressure in each tank. We can use a tank of compressed air to perform useful work using this same basic principle. If we connect the tank with 100 psi to a cylinder, the air will flow into the cylinder, and the pressure will build up until the resistance on the piston is overcome, and then the piston moves. In this type of system, work will continue only as long as the pressure on the piston area is enough to overcome the load. But while air is flowing out of the tank, pressure in the tank is dropping. To get any appreciable amount of work out of a system, we must use a device to supply the tank with a sufficient amount of air at a desired pressure. This device is a compressor. The one you're looking at is a positive displacement type compressor. There are several types, and we'll look at them in detail in Lesson 5. It takes energy to drive a compressor, but when we use pneumatics to perform work in a system, we never get out as much energy as we put in. This is due to inefficiencies in the system. The energy loss is usually in the form of heat. When the air is compressed, it gets hot, and when it flows through pipes, it rubs against them, and this friction also causes heat. So some part of the pneumatic energy is transformed and lost before it even reaches the actuator. The ratio of the energy available at the output of the actuator divided by the energy put in to drive the system gives us the efficiency of the system. Now let's talk a few minutes about measuring compressed air. As we have stated, air is compressible, which means that for a given block of air, as its pressure goes up, its volume goes down. Remember our formula, P1 times V1 equals P2 times V2? So a block of air, 1 cubic foot in volume, near the intake of the compressor, where it's at atmospheric pressure, will have a much smaller volume, like this, when compressed to 100 psia. As you see, there is a wide variation in volume with changes in pressure. So when referring to flow rates or compressor capacities, we must use what is known as standard air. Right here I should explain the difference between standard air and free air. Free air is a common term and means air available to the intake of a compressor. Since the condition of free air varies from day to day and location to location, we need a way of describing air that is consistent and never changes. This we call standard air. A standard cubic foot of air is defined as a cubic foot of air at 29.92 inches of mercury, or 14.7 pounds per square inch absolute, whichever way you want to state it. Also, its temperature is 68 degrees Fahrenheit, and it has relative humidity of 36%. Relative humidity is a measure of how much moisture is in the air. From this point on in this course, we will use the term SCFM, which means standard cubic feet of air per minute. Okay, let's look at velocity. Velocity is the speed at which a thing is moving. For example, when we say an automobile is moving at 30 miles per hour, we are stating its velocity. In our case, it's air we are talking about, and its velocity is usually measured in feet per second. Let's say we have a system requiring 520 SCFM of air, and through one pipe, it will move with a velocity of 100 feet per second. Through a smaller pipe, with say 1/2 the cross-sectional area, we can still get 520 SCFM. But now the air must travel twice as fast, or 200 feet per second. We can make the pipe even smaller and still get 520 SCFM through, as long as there is enough pressure difference to shove the air through faster and faster. There is, however, a limit to how fast air will flow. This is called critical velocity. The critical velocity for air is the speed of sound, which at normal temperatures is approximately 1,100 feet per second. And if you have a cylinder that must operate extremely fast, care must be taken to have the lines large enough to keep the line velocity down to a reasonable figure if the unit is to work satisfactorily. This ends Lesson 3. If you will turn in the text to page 24, you will find a brief review. And on page 25, there is an exercise which will help you to determine just how much you've learned. I'm Dave Brown for Teletrain.